So now it's recording. Let me reshare the screen again. Hopefully you guys can see that again there. So this week, or at least last week, you guys did circular motion, right? So I'm going to be reviewing just kind of the lecture slides and giving my own overview of what's going on from the past week. So I'll go over all the lecture slides, and these are Dr. DeJong's lecture slides. I know for other professors, you might have slightly different or totally different slides, and you might have understood what was going on, you might have not. It is what it is. So I will try my best to kind of reinforce the concepts that you guys went over last week, and then we'll do some of the online homework problems that I didn't go over in my last session, as well as a quiz, like a sample quiz at the end. So hopefully you have time for everything, and I'll try to manage time as we go along. So without further ado, I think we can go ahead and start. Section 1, Introduction to Rotational Motion. So for rotational motion, two varieties: circular trajectory, extended object moving, rotating around an axis. So if you remember the online homework, this was a clear example that we had. There's a pivot, right? So for example, there was that online homework problem about the astronaut, and they were kind of spinning around in this like device, right? And so for the circular motion, you could either just be moving in a circular pathway, right? If you're making a turn, for example, or if you're walking also is kind of a circular motion in a sense, and we'll go over that here in a sec. But basically, for rotational motion, you either have that circular trajectory, or you can have some kind of object, right, kind of spinning or pivoting or moving in a circular motion around a specific axis. So in this example here, you can either be moving circular pathway, right, moving, turning or something in a car or whatever, or you could be kind of spinning around an axis, right? So like think of a DVD player or a CD player. They're spinning that CD or DVD around a specific axis, like a central axis, right? Or a pivot is what we call it. So if the speed of that rotation is constant, right? So if we're not changing the speed at all, if we're moving at a constant 20, 30, 40 meters per second, 20, 30, 40 miles per hour, right? If that speed is constant throughout the entire like time interval, right? So if we go 0 to 30 seconds, we're constantly moving with 20 meters per second or 3 centimeters per second or whatever it is. If we're not changing our speed, we're moving at what's called uniform circular motion. So think of uniforms like at schools. Uniforms, they're all the same. Everyone wears the same stuff with uniform circular motion. Everything, the entire interval, everywhere around, it's the same speed. Now, that doesn't mean we have the same velocity, though. So if we don't have the same speed all around, then the motion is non-uniform, and we really don't have a lot of cases where we're doing circular motion that's not uniform, and so you don't really have to worry about that a bunch. But as we can see here, right, if we have constant speed everywhere, right, we might be traveling 20 meters per second all around at every point in the circle, but we're constantly changing direction. So if you remember the relationship between velocity and speed, right, so the magnitude of velocity is our speed, because velocity, if you can just think about it, is just speed with a direction, right? So if we're moving negative, 10 meters per second here, we're moving positive 10 there, right? But we're still moving 10 meters per second in general, right? So our speed is constant, our velocity is constantly changing, though, because we're always changing direction. We might not necessarily be changing like the magnitude of the velocity or magnitude of the speed, because we're keeping constant speed. But the issue here is that we're changing direction all the time. So remember, for acceleration, I stated this in the previous session and in the first couple of weeks as well. So acceleration kind of comes in two flavors. You either have a change in direction, right, or change in magnitude of velocity. So change in direction of your motion, or a change in your magnitude of velocity. So I could either be going, let's say if I go 10 meters per second to 20 to 30, right, then I'm speeding up. So I have an acceleration maybe in the positive direction. Now I could still be going 10, 10, 10 and still accelerating. And that's what we have here, right? So I might be going 10, 10, 10, uniform circular motion, keeping the same constant speed, but I might be going southwest here, south here, east there, north here, northwest, so you're constantly changing direction. Now, for, like I said, this is just kind of a repeat. Speed and magnitude of the acceleration are constant for uniform circular motion. So speed, like we said, constant speed, you're moving with the same speed throughout the entire interval, right, at every single point in the circular motion, and you have the same magnitude of the acceleration as well. So acceleration will be constant in its magnitude, differing in its direction. So if I'm going here, right, moving south, my acceleration, like we know for centripetal acceleration, is pointed towards the middle. So it might be pointing exactly east here. Maybe it's northeast here. Maybe it's south there. Maybe it's northwest, right? It's constantly changing direction, but it might be a constant 4 meters per second squared, for example, or 5 meters per second squared. But here might be negative, might be whatever, like you might have a direction associated with this one. Up, down here, you have down here, it'll be straight up, so it might be positive, right? So it's constantly changing direction, but it keeps a constant magnitude. And acceleration for uniform circular motion, like we said, centripetal acceleration is pointed towards the circle center. So when we have that acceleration pointing towards the center, we call that centripetal acceleration. And that centripetal acceleration is equal to v squared over r. So v being the speed that you're traveling at, and then r being the radius of your circular motion, right? And so acceleration in uniform circular motion, it's entirely centripetal. In non-uniform, you might have additional components. So if you're not traveling at a constant speed at every single time interval, every single point on that circular pathway, you might have a centripetal component and then also maybe like an additional component. So if like say here, I decided to like speed up at this point from like 20 meters per second to 30. So I'm still going to have some component of centripetal acceleration, but I'm also going to have like some acceleration vector that's going to be in the direction that I'm speeding up. So I'm speeding up in this direction, then I might have acceleration in that direction as well, along with this centripetal acceleration. And so then my overall acceleration vector would be kind of maybe like this. So it wouldn't be directed exactly towards the center, right? But it's still pointing inwards. It's still allowing a rounded, if you will, or somewhat circular motion. But since you sped up somewhere along the interval, your acceleration isn't exactly solely centripetal. But that's non-uniform motion. Like I said, we're not going to worry about that. That's just more like for you to understand the concept. So if you're centripetal, uniform, right? If you're moving in uniform circular motion, all your acceleration is centripetal. If it's non-uniform, right? If you're not traveling at a constant speed, you're going to have some components that are centripetal, right? Pointing towards the center. And then other components are, pointed in whatever direction you're moving, right? Or, for example, if you're slowing down, like if you're moving in this direction but you're slowing down, then your acceleration is actually opposite, right? Because if you're slowing down, if you have, let's say this is positive velocity, then you'd have to have negative acceleration to slow you down. And so maybe your acceleration is pointed this way, right? That's your additional component along with the centripetal component, right? So it's AC. So then maybe you might have a acceleration that's kind of like this or whatever, like, right? So it's just, that's what you have when you have non-uniform. But like I said, most of the problems are going to focus on uniform motion. And then with regards to figuring out velocity and acceleration on the centripetal pathway, right? So your velocity vector is always going to be tangent or directly next to or adjacent to the curve, right? So if I'm here, velocity is around, I can think about this like this circle as being, I can think about this circle as being kind of my displacement, right? So if I take the slope, take the slope here, basically I can see that velocity here is towards this way. Here it's this way. There it's this way. Like that, So it's just adjacent to the curve. Now, acceleration, like we said, since it's uniform circular motion, centripetal acceleration is always pointed radially inwards. So always pointed along the radius towards the exact center of the circle. So, and yeah, velocity is not constant because velocity is speed with a direction. So if our direction is constantly changing, if we're going from east to south to northwest to northeast, whatever it is, then we're changing the direction and therefore we're changing our velocity, right? Now, here's a quick example. Car is turning a tight corner, constant speed. So if we know constant speed, that means uniform circular motion. Top view of the motion is shown in the figure below. Velocity vector for the car points to the east, right? So we know if we're, imagine this was our circle, right? Then velocity vector is tangent, right? So it's east here. Velocity vector for the car points east. Okay, what is the direction of the acceleration? So since we know it's constant speed, that indicates uniform circular motion. So we know that our acceleration is centripetal acceleration. That's the only acceleration really in play at this point when we have uniform circular motion. And if it's pointed towards the center here, Well, that's south based on these like cardinal directions, right? But yeah, same deal here, right? If we have this ball, right, and we're kind of spinning it above our heads, right, on a string, then this ball is going to keep going round, 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 round. If we were to cut the string when the ball was at this point in the trajectory, right, what the question is asking here is like, what direction would it go in, basically? Like, if we were to cut the string at that exact instant, that exact moment, what direction would the ball just continue to fly in, basically, or go in? And so that's dependent on its velocity, right? So what's its intended motion? So if I'm right here, right, in that circular pathway, then my velocity is just tangent to that curve right there. So I would, if I'm going this way, right, counterclockwise, then my velocity would be in the direction of B. Now, if I was going clockwise, for example, if I was going this way, then it would be, the velocity would go that way, right? So if I were to cut the string as I was rotating it or spinning it clockwise, then if I cut the string here, then it would go flying kind of southeast, basically. As opposed to if I was spinning it counterclockwise, then it's moving this way. And so if I cut it when it's moving this way, then it's going to go flying northwest, basically. It's going to continue in that straight path that is tangent to the circular pathway. So velocity tangent to trajectory. And so if you just take away this string right here, it just continues moving in whatever direction is tangent to the circular path, right? Now we get to like period, frequency, speed, stuff like that. So this was a majority of what you're going to see in your online homework, written homework, and stuff like that. So for circular motion, a lot of it is this period, frequency, and speed stuff. So period, right, is the time interval it takes for an object to go around a circle one time. So it's the amount of time it takes to make exactly one revolution, to travel exactly once around this circle, right? So if I'm traveling around this circle, right, what does that equal to? It's equal to the circumference, right? So it's equal to just kind of the perimeter, the distance around the circle, right? And so basically I'm trying to figure out, well, if this total circumference, for example, is 30 meters, right, then how long does it take me to travel 30 meters? That amount of time is equal to my period then. Period is equal to the amount of time it takes for you to travel exactly once around the circle, to make exactly one revolution. So that's where you're going to see your revs, right? So if, for example, I have 3 revs per second, well, that's a little different, right? Because I know then in 1 second I'm traveling, 3 times basically around the circle. Now, if I wanted to figure out how many times it would, or how long would it take to travel 1 revolution, right? Well, we can say 3 revs is equal to 1 second. Well, how many seconds does it take to travel 1 rev, basically? And so you can just kind of do your ratio there, and then figure out basically how many seconds it takes to get to 1 rev, basically. So that's the concept there. 3 revs per second gives us frequency. So it's the number of revolutions per second. So frequency is revolutions per second. It's the amount of times I can go around a circle per second, right? And so that's a distinction that you have to make here. Now, frequency is equal to 1 over period. So that's the equation that we have here for frequency, right? So if I were to say like, all right, 3 revs per second is my frequency, right? And it takes me, let's say, 5 seconds to go around, It takes me 5 seconds, for example, to go around, or actually, I take it back. I take that back. Sorry. So if I was trying to figure out how long it's going to take me to travel 1 second, right? Or how long it's going to take me to travel around the circle once, then I'm calculating for my period, so that I can do that, multiply it over, and so I get period is equal to 1/3, right? So it might take me 0.33333 seconds to travel once around the circle. So I can use my equation here, frequency is equal to 1 over period, to figure out either one, right? So if I were to also say maybe frequency is equal to 1 over our period, let's say our period was 3 seconds, right? So it takes us 3 seconds to travel once around the circle. then in this case, our frequency would just be 1/3, right? So this would be like 0.33 revolutions per second, basically. So that's the relationship that you have here between frequency and period. So now we're trying to relate speed, right, with frequency, with period, with the distance that we're traveling around the circle, right? So it's a little bit more complex, right, because we have this speed. We know that speed, just based on previous knowledge, is going to be like your displacement or distance over time, basically, right? So this distance that we're traveling is the length around the circle. Time is the time interval, right? So the length around the circle is going to be equal to your circumference, right? It's the perimeter, it's the distance around the entire circle. So your circumference is 2 pi r, right? So if we're talking about the length or the distance around the circle, it's the circumference, it's 2 pi r. That's the length or the distance that you travel per time interval, right? Now, what is the time interval? Well, the time interval is going to be, for example, our period, right? So period is, like I said, period is the amount of time it takes you to travel one revolution around, right? So delta t is our time interval. This is our speed, right? This is the same as kind of saying like v is equal to x over t, right? Instead of x, we know that it's the length, and so our length is the circumference, basically. So now we can kind of relate this equation to circular terms, right? So if we know the length is 2 pi r, right? That's our circumference. It's the distance around the circle. Then we can say it's 2 pi r and then divided by t, right? So t in this case is our period. It's the amount of time it takes us to travel one revolution. So that makes sense, right? Because if we say like this is our circumference, right? And then let's say our t here is 1 second. So then we say for our speed, oh, it took us, let's say for example, 3 meters, and this is per second. So we're traveling individually at every single point 3 meters per second. Now that's different from our frequency. It's different from our frequency. Our v here kind of indicates what the speed is at every single time interval here. So if I look here, it's 3 meters per second. Here, it's 3 meters per second. There, it's 3 meters per second. So that's my speed. Now, if I'm talking about my frequency, it's a little bit different. It's the amount of times I can go around the circle per second, right? So speed is just individually at every single time interval, right? Or every single point around the circle. How fast am I traveling in terms of like how much like distance I'm covering per second. But your frequency is how many times can I go around that full circle per second. So like it gets confusing then when they in a problem they ask you like how fast you're going, but usually they'll indicate like, okay, how fast are you going in revs per second, so revolutions per second. Well, if it's revolutions per second, it indicates frequency, right? Now they would ask you how fast you're going in meters per second, then that indicates speed. So speed, meters per second, frequency is rev per second, right? So that's a really important distinction there. Now, you can see here, since we have divided by t, well, the reason why we can say it's 2 pi r times frequency f, right, is because f is equal to 1 over t. So this is saying like 2 pi r times 1 over t, which is the same as dividing by t, right? And so this just becomes f, 2 pi r f, right? So if, for example, they just gave you the frequency, you can just multiply in the frequency instead of having to find the period and working backwards to do that, right? So yeah, this is kind of the setup here for figuring out speed relative to the circular information that we have, like our circumference and the period and stuff like that. Once again, this is an example problem, so if they give us revolutions per minute, we got a really important part of this unit is identifying like what units mean what. So like I said, revolutions per minute, revolutions per second, that's any like revolutions per any time interval, right? Per milliseconds, per microseconds, whatever it is, that's going to indicate frequency. If I'm saying like meters per second, miles per hour, right? Well, that's an indication of speed, linear speed, right? Now, that's one of the most important like distinctions that you have to make, especially with this unit's information. So if we have hard drive disk rotating at 7,200 revolutions per minute, disk has a diameter 5.1, they're asking us what is the speed at 0.5 centimeters from the center axle. Well, the center axle is here, 5 centimeters from it, right? We can think about that as our radius. So the diameter here is just totally irrelevant, because the reason why is, okay, well, diameter, you might think if we divide it by 2, oh, that gets us our radius, right? So let's say let's say if it was 6 instead, right? If this was, just so I can make it easier for the calculations, if this was 6, or actually no, I take it back. This is just inches and centimeters. So let's say this was 14 centimeters instead, right? So then my diameter would be, my diameter is 14 centimeters. My radius then would be 7 centimeters, right? So that's the radius of the entire disk is 7 centimeters. So from the center all the way up to the edge of the disk is 7 centimeters. But they're not asking us about the entire radius. They're just asking us what is the speed at a 0.5 centimeters from the center. So it's saying okay, well, if this whole thing is 7, well, what's the speed here at 5? That's what they're asking. And so in that case, your radius would have to be 5. So it's dependent on what area you're trying to figure out. So radius is 5 in this case. And then they're also asking us for acceleration at this point on the disk, right? So for speed, we have this equation here, 2 pi r over t, or 2 pi r times frequency, right? So we have 2 pi, we have our radius that we're interested in, and then we have our frequency directly. So there's no point in trying to convert frequency to period here using the frequency is equal to 1 over t equation. You can just literally just plug this in. Now the only thing that you have to adjust then is to make sure that everything is in meters per second at the end, preferably, unless the problem asks you to have it in different units, but usually it's going to be meters per second. So that means you take your centimeters, convert that to meters, revolutions per minute, make them revolutions per second. So we want it to where we have meters and we have seconds, right? So if it's revolutions per minute or revolutions per hour, convert it to revolutions per second. And if it's centimeters or micrometers or whatever, convert it to meters. That way you can get your final answer in meters per second. Now, if we're asking about acceleration, well, we know that centripetal acceleration, right, is going to be v squared over r. So we just take our linear speed that we traveled at, square it, divided by our radius that we're interested in, and that was 5 centimeters, not the 7, just the 5. And then that way we can get our centripetal acceleration. But yeah, that's kind of an overview for the the speed, period, frequency stuff, and just kind of basic information about centripetal motion. Now, when we have a centripetal acceleration, right, well, according to Newton's second law, we know that F equals ma, right? So when we said earlier that if I'm traveling in uniform circular motion, my only acceleration that's in play is my centripetal acceleration. Well, if I wanted to set up a net force equation, for example, and my only acceleration is my centripetal acceleration, then I can say that, okay, F is equal to ma, and that a is just equal to centripetal acceleration, right? So it's mac then. So we have to make this unique distinction now to where F equals mac, well, what is that force? We call that a centripetal force, right? So centripetal force isn't like an entirely new force on its own. All it is just kind of a description of what's going on in a sense. And so, for example, like if you remember, this is kind of like retrospective analysis. So if on your problems, right, if you had like static friction towards the middle or something like that, or gravity or whatever it was on your problems, right, then that force pointing towards the center, we call that our centripetal force, right? That force towards the center is our centripetal force. So it's kind of like more or less just kind of an adjective for an existing force. So it's not like a whole new unique force. It's just a description that the force that is acting towards the center, right, is giving us a centripetal acceleration, allowing us to move in a circular motion. We call that a centripetal force. It's the force that allows us to move in a center or circular type motion, right? And so for our centripetal force, we denote it Fc, and that's equal to mac. So it's the mass of the object times the centripetal acceleration that we have there, right? So like I said, it's not a new force. It's the name for the net force in circular motion, right? So if our net force, let's say F net, right, let's say if that was like, if it was a roller coaster ride, right? And you're at the bottom, you're at the bottom here. Then you have Fn towards the top, Fg pointing towards the middle, or outside, right, or to the bottom. So we have F net is equal to Fn minus mg. And then we know that there's a circular pathway involved, right? And so in order for there to be a circular pathway, we have to have centripetal motion, and we have to have centripetal acceleration, therefore. So this is all going to be equal to MAC. So in this case, our centripetal force, quote unquote, right, is just a name or a description of the forces, or the net force, right, that is going to be offering us a circular motion, basically. So it's not an entirely new force that you have to name or consider or anything like that. It's just more or less a description or a specific like adjective or description for the forces or the net forces, right, that are giving you a circular motion. So like we've seen Fn minus mg before, right? So why don't we call this then, like our net force, why don't we call that centripetal force, right? The reason why is that in those other cases, we're not having motion in a circular path. So once we have that motion in a circular path, right, then whatever components are contributing, right, to that circular motion, we give them or denote them with an F net that is a centripetal force, right? So it's more or less kind of an adjective to describe forces or components of forces, right, that are particular or help offer some kind of circular motion, right? And then we know from AC acceleration, centripetal acceleration, that's equal to v squared over r. So in this case, MAC is equal to mv squared over r, right? And so here's a quick check problem. If we have the ball at the end of the string being swung in a horizontal circle, what force is providing the centripetal force? Well, if we have the ball here, there's gravity pulling it downwards directly, and then there's tension force because we're spinning the ball around in a circle, basically, right? So that tension force, think of it, there's a circle, right? It's pointing along the radius, pointing radially inward, right? That's going to be what's offering us centripetal acceleration, and that's what's going to be offering us centripetal force, right? So there's Fg and there's Ft, right? Well, in terms of the circle, like what's directly involved in the circle? Really, it's just Ft, because if we look at, for example, if we were to say this is F net x and F net y, well, F net x is equal to Ft only, right? There's nothing else in the x direction per se, right? So that's also going to be equal to our centripetal force, right? So the net force here is centripetal, right? Because Ft is providing or helping to provide a circular path. Now, F net y, for example, well, that's just Fg, right? Because there's nothing else here that we have in question. And that's not going to be offering any type of centripetal force or centripetal acceleration, right? It's still acting on the ball, that's for sure, but it's not directly in play or in consideration when we're talking about what's giving us a centripetal acceleration or centripetal force. So the tension of the string is the only thing that's in question here that is playing into this centripetal or central like circular pathway. Now, if for example we had something else, like I don't know, like this is just not right, but let's just say like some other force, right? Some other force. Then our F net would be, let's say, Ft minus F, and that's all equal to MAC. Because then we have to consider, well, Ft is the one that's directly providing the centripetal acceleration and therefore the centripetal force, right? Because it's pointed towards the center of the circle. But at the same time, it's kind of like it's being held back by the other force. So the other force is directly affecting what type of centripetal force we can offer. And so that's why we would include that other force in the equation, because it's directly factoring in to what our overall centripetal force or net force is going to be. Because in that case, like if Ft was 50 newtons, right, and F was 10 newtons, then, well, if we didn't have that force, it would be F net is equal to 50 newtons, right? And that's equal to our centripetal force, which is tension, right? Now, if we had that other force, right, it would be like 50 minus 10, so that'd be 40. Well, then that decreases our overall net force or our overall centripetal force, right? So we would then be considered with like the forces along the same axis as the force that is directly providing the centripetal acceleration, right? So in this case, the force that's directly applying the centripetal acceleration is the force that is pointed towards the middle of the circle. So we know that's tension. If we were to have anything else, that's not necessarily like providing a centripetal acceleration or centripetal force, but it's affecting it, right? And so that's why we'd include it, or that's why we would kind of factor it in, because it's on the same axis and it might decrease or increase or whatever the overall net force and therefore the centripetal force. But yeah, now when it comes to these types of problems where you have kind of some kind of circular motion here, especially with a car or whatever, then it says engineers dips and peaks and roads to be segments of circles, the radius that depends on expected speeds. A car with mass m is moving at a constant speed and goes into a deep dip in the road. We know that constant speed here indicates uniform circular motion, right? So we're going to have a centripetal acceleration, especially since we have this circular pathway. And at the very bottom of the dip, how does the magnitude of the normal force compare to the car's weight, mg? Well, we know that normal force is acting upwards here, right? Because this is the surface of contact. Normal force is pointing upwards, gravity is pointing downwards. So if we were to set up an F net, right, and like I said, that's going to be our centripetal force, then we have Fn minus Fg, right? Now, the thing is this normal force, right? Remember, that's going to be the one that's directly like providing a centripetal acceleration, right? And so then we can say this is equal to MAC or mv squared over r, right? So then if we want to look at it, how can we compare Fn to Fg? Well, we can say that, okay, Fn is then equal to mg plus mv squared over r, right? So that means that gravity plus the overall net force or overall centripetal force is going to be, or like gravity plus that is going to give us normal force, right? So that means that gravity is then less than normal force. Because if this was 60 newtons and this was 50, right, and this is 10, for example, you can see that these kind of combine to make this larger force. So mg, the force of gravity, would have to be less. And that makes sense too in terms of free body diagrams. If we didn't have all the information and we were just looking at this logically, right, or using our intuition, well, if we're traveling in a circular pathway, we must have a centripetal acceleration. If we have an acceleration, right, based on Newton's law, Newton's second law here, right, F equals mac, well, if that centripetal acceleration is, for example, positive in this case, right, so it's pointing, remember, centripetal acceleration is going to be pointing towards the center of the circle. So if we were to kind of continue this, imagine this is the circle pointed radially inwards towards the center. Well, that's along the positive y-axis, right? So that means that our net force should be positive, right? So if our net force is positive, then we would have to have the force in the positive direction overwhelm the force in the negative direction. So therefore Fn has to be bigger than Fg, because if it's bigger, right? If this was 60 newtons and this was 50 newtons, right? Then remember our net force equation would be 60 minus 50. That gives us a positive 10 Newton force upwards, right? And so that's kind of another way to determine it more logically instead of like numbers and stuff. So we have to look at what direction is our centripetal acceleration, right? Where's it pointed at? Towards the center of the circle. Where's the center? Oh, it's upwards like this. So if acceleration is positive in this case along the positive y-axis, then we must have a positive net force. If we have a positive net force, right, then the forces in the positive direction must overwhelm the forces in the negative direction. And so normal force then has to be greater than gravity. So we have a question here, would our apparent weight make us feel heavier at that point too? Yeah, absolutely. So in this dip here, since your normal force, right, is greater than gravity in that case, right, we know that normal force, or at least apparent weight, is the sum of all contact forces. And the only contact force that we have here is normal force, right? So if normal force is greater than gravity, then our apparent weight at that bottom dip is going to be greater than our actual weight, right? And you can see that because if normal force is 60 and gravity is 50, for example, right, that gives us that positive net force that we want, that is going to give us or allow us to move in that circular path. And at the same time, we can see that since our normal force is greater than gravity, our apparent weight is greater than our actual weight? Yep, excellent question. But yeah. Yeah, you can see here, this is just kind of a reinforcement. Since we have that net force upwards, because we have that centripetal acceleration pointed upwards, right, towards the center of the circle along the positive y-axis, well, based on F equals ma, if A is positive, then F is positive. And if F net is positive, right, then we have to have the forces in the positive direction overwhelm those in the negative direction. Now, this type of problem here is concerning maximum walking speed, right? So when you're walking, I actually never knew this before, but essentially when you're walking, you kind of have this circular type motion, or at least I guess I never really thought about it necessarily, but it makes sense. So if we are walking, right, we're gonna have this circular type stride, right? And so when that's occurring, we have to look at what forces are acting on our bodies, right? So we have gravity, obviously, due to our weight, and we have normal force, which is the contact force from the surface that we're walking on, back on us, right? That's Fn minus Fg, right? Now, as you walk, right, well, if we were to set up a F net equation, let's say F net is equal to Fn minus Fg, well, based on the fact that we know that when you're walking, you have this circular type motion or circular type stride, then if you have circular motion, you must have a centripetal force giving you that circular motion, right? And those components that are factoring into the centripetal force are Fn and Fg. Now, more directly, right, since it's like this, and if this was our circle, then Fg is the force that is directly contributing in a sense. And normal force would almost kind of be acting against it in a way. So this would be, there's actually be negative mv squared over r here, right? I like to integrate my directions. The reason why it's negative here, right, because if this is the circular type motion here, this was our circle, centripetal acceleration points towards the middle of the circle, and it's pointing along the negative y-axis, right? If it's pointing along the negative y-axis, then our acceleration is negative based on F equals ma. If acceleration is negative, then force is negative, right? If our F net is negative, right? Since we have circular motion, remember the net force is our centripetal force. So if F net is negative, then Fc is negative. And so if Fc is equal to mv squared over r, and it's negative, then we just add a little negative sign, negative mv squared over r. And that gives us this idea here. Now, what this situation is kind of asking you about is to determine what the maximum speed is, right? Well, if I want to look at my maximum speed, right? If you imagine, you start walking really, really fast, right? After a while, or after trying to up your speed for whatever time interval, right? You get to a certain maximum speed. And what happens at that maximum speed is you start to kind of feel lighter as you increase your speed, right? So think about you trying to speed walk or something. First, you kind of obviously feel contact with the ground. That's normal, right? But then after a while, as you try to move faster, well, then you're okay, well, if I walk any faster than this, you kind of feel like you're about to levitate or you're about to just lose contact with the floor, right? And so if you levitate or lose contact with the floor, then you lose your contact surface, and therefore your Fn is equal to 0. Your normal force would equal 0 if you lose contact with the surface. So when they're asking us for maximum walking speed, they're asking us for the speed at which you're basically just about to lose contact with the floor that you're walking on, right? Because you can only walk so fast before you have to then run, right? Because otherwise, you keep walking, right? As you walk faster, normal force decreases. Well, how does that occur? Well, if we want to look at normal force and how it depends on your speed, well, Fn is equal to mg minus mv squared over r. So if we continuously increase speed, increase, right? Then let's say if this was 30 newtons, right? And it was initially, let's say 10 newtons for mv squared over r, right? If we increase the speed and it becomes 20, for example, then we went from an Fn of 20 newtons, first of all, 30 minus 10 is 20, to now an Fn of 10, right? So as you increase your speed, you're going to decrease your normal force, and therefore, when you walk faster, you tend to feel a little bit lighter right? And you kind of start to lose contact with the floor. So when you're asking about maximum walking speed, we're looking at basically how fast can we go before we start to like lose contact with the floor. So the faster you walk, the lighter you feel. And so that means if you feel lighter, your apparent weight is decreasing, right? And so as you walk, you kind of get lifted up a little bit. So you can see here, you kind of get lifted up off the floor in a sense. So if you walk too fast, you're just going to start levitating, I guess. So that's one way to get your acceptance to Hogwarts. So, yeah, that's pretty much what's going on here. Now, if you wanted to directly figure out what the maximum speed here is, well then, if we know that the maximum speed means that you lose contact with the floor, then Fn is equal to 0. So if Fn is equal to 0, then we can just set mg is equal to our centripetal force here, mv squared over r, and then solve for v, right? So times r, we divide by m, so we have rg is equal to v squared, take the square root, so square root of gr is equal to v. But yeah, with this type of example here, now think about a coin rotating at a constant speed. So constant speed makes or means that we have uniform circular motion, right? Now it moves without sliding here, right? So if it's not sliding, then there has to be some force that prevents it from sliding, prevents it from slipping, right? So if there's a force that prevents it from slipping, like if it's static, right? Because if it's just there, sitting there, moving around, right? It's not sliding across the floor. It's just staying static. But there's a force that prevents it from slipping. Well, that force is static friction, right? Because we can think about static friction force as the force that prevents sliding or slipping, right? Now, if we're to think about this, this is such a weird way to kind of look at this because this is 2D. But if you were to look at a record player or something, or a record, right? Let's say this is kind of like a cylinder, right? Let's just look at a cylinder. This is our record here, right? Now, directly downwards, like through the actual record itself, let's think of this as the 3D plane, right? We have FG. Up top here, we have FN, right? Those cancel out. This thing isn't levitating, right? It's just constant along the y-axis. So they should cancel out. Now, in order to keep moving in that circular motion, right, what force should we have that provides that circular motion? Well, the only force that's acting on it to prevent sliding or slipping is static friction. And so static friction would then have to act this way towards the center of the circle, right? Giving us centripetal acceleration and therefore allowing us to continue moving in that circular pathway, but also at the same time without slipping. So it allows us to move in that circular motion, but also without slipping. And so the other forces that are along the y-axis, Fn and Fg, they're not along the same axis, so they don't directly factor into our centripetal force or our net force or whatever. They don't directly offer us a centripetal acceleration. So we're concerned with the forces that are pointed towards the center of the circle or along that radius, right? So if I have static friction here, right, as my only force, that's the force that's preventing me from slipping or sliding, right? Then that's what's going to offer centripetal acceleration. That's what's going to keep me moving that circular motion. And then yeah, basically we just prevent it from slipping off as well. So it keeps you moving in a circle and it prevents you from slipping off. And so you'll see a lot of these record player type problems or CD type problems. And so static friction is always kind of pointed towards the center here. If the object, if the coin or whatever is not slipping, right? Static friction force pointed towards the center here to allow circular motion, also prevent you from slipping. But yeah. Same deal here for a car, right? So if we were to look at this car, we know that along a 3D plane, we have normal force pointing upwards, gravity pointing downwards, right? And then, like, this is as if we were looking from behind the car. So, like, if the car was making a right turn, basically, right? Then we know that normal force is pointing upwards, gravity is pointing downwards, and then, like, static friction force, which is the grip force, right? It's the force that allows us to make that turn. Remember, I said that at the beginning of the semester. This is where we're getting into it. Static friction force is like our gripping force, right? And provides acceleration, centripetal acceleration. and a centripetal force, therefore, towards the center of the circle. So this is if you were looking behind the car. Now, based on like the drawing that we have here, since this is our circle, centripetal acceleration is pointed towards the middle of the circle, right? So it would be directly downwards, like this, right? Towards the center of the curve. And then what force provides the necessary centripetal acceleration? Well, that's static friction force, right? Static friction force is the grip type force that prevents the tires from slipping and sliding. It allows us to grip with the road and helps us to make that turn. So this is just kind of like a know it and this is how it kind of is almost type situation, right? So static friction force provides you that grip type force to allow you to make a turn and allow you to move in a circular path and prevent the slipping or sliding of the car. Yeah, go ahead. No, go ahead. With a car, it'll never be kinetic friction, or almost always will never be kinetic friction, because kinetic friction is like if you have the if an object is kind of like sliding across the surface. So maybe, I guess, like since static friction force, like we said, it's kind of a grip type force, right? Well, I guess maybe if you have like ice on the road, for example, you kind of lose that grip. Or if your tires didn't have a lot of grip to them, for example, then you'd kind of be sliding in a sense. And that's what kind of happens too. Like if you're in the snow time, right, you kind of start slipping and sliding with your car, and that's dangerous. So, but yeah, and in the car type problems, you never have kinetic friction. You almost always have static friction as the force that is preventing slipping or sliding and giving you that grip along the surface. Now, I'm trying to think of maybe a different situation like that would give you kinetic friction. But yeah, I'm trying to think. I don't think there are any like notable examples that we did with kinetic friction as our centripetal, or the force that is directly giving us centripetal acceleration and therefore centripetal force. But maybe, I don't know if this is quite accurate, but I guess depending on the situation, like if we were to have maybe a snowboarder, right, or something like that, and they're making like a sharp turn, well, they're on ice and the snowboard is like sliding on ice, right? There's no grip really to that snowboard. And so in that case, to be able to kind of move in that circular type motion, I guess then maybe kinetic friction would be pointed towards the center. But I'd have to check up on that one. But yeah, you usually just use this static friction in these types of problems where you have like a car or something, and they haven't tested us at all about like kinetic friction being the force to offer you any centripetal acceleration. But I'll look into that just to check and see. Maybe I'm just missing something or I forgot. But yeah, I'll get back to you guys on that one. I'll maybe send like an update in the group me or something. But yeah. Now, let me see what's left here. So, okay, there's a decent amount left, but yeah, I'll try my best. Okay. No, I haven't. No worries. Yeah, I haven't. Yeah, no, I figured I'd try and give more of a conceptual explanation of things, of what's going on, because I figured that's more important than just solely practice, because you can have a lot of practice problems, but if you don't understand what's going on, then it's tough to even solve them. But yeah. Now, for this type of problem where they're asking us about maximum speed, right? So for maximum speed with a car, right, it's a speed that we can go at without the car sliding. So when the car's just about to slide or slip, right, or just before basically, right, that's when we're traveling at our maximum speed, and that's also when we have static friction force at its max, right? The static friction force is at its maximum when an object is about to slide or slip. So when we're looking at how fast we can go before it starts sliding or slipping, right, that's our maximum speed. When they say maximum speed without sliding, that means like how fast can we go before like this stuff starts to slide and slip. Because if we were to go any meter per second or centimeters per second over, then we're about to slip, or we're going to slip basically. So when we're concerned with maximum speed without sliding, then we're looking at how fast can we go without slipping, or if about to slip basically. And so that's when we have static friction force at its maximum. And so we have all this information like radius and the mass of the car, and we have the coefficient of friction here, and we're trying to figure out the speed, right? So for this circular type turn, right, we know that we're going to have a centripetal acceleration pointed towards the middle of the circle here, right? Now, we know that centripetal acceleration is equal to v squared over r. So that's the first thing that you can figure out. Well, okay, since I know I'm going to be moving in that curve, right, I have to have a centripetal acceleration, and I know that speed that I'm traveling at factors into that centripetal acceleration. Well, how can I relate centripetal acceleration and the speed that I'm traveling at to the rest of the information that I have? Well, I know that if I have a centripetal acceleration, I must have a centripetal force, right? Well, then if I want to figure out the speed that I'm traveling at, right, then I can use information about forces, right, that are going to be offering that centripetal acceleration, and then therefore causing, or I guess since speed factors in acceleration, so the speed that I'm traveling at gives me that centripetal acceleration, and so I want to figure out the forces that contribute that to that centripetal acceleration in a sense, and that's how I can figure out the speed. So if I know that my net force or my centripetal force is equal to MAC, well, the only force that's acting in the middle here, right, or along that axis that's going to be providing me with a centripetal force is static friction, right? And so I know that at its maximum speed from before, based on the interpretation of the problem, maximum speed, fastest I can go without slipping or sliding. And if I'm just about to slip or slide, then static friction force is at its maximum. So therefore, I can actually say that it's equal to mu times Fn, right? So then I can say mv squared over r is equal to mu times Fn. I want to figure out my speed. I have my radius, I have my mass from before, I have my mu, and I can get my normal force, right? Because normal force, since this object is in contact with the floor or the road or whatever, right? And it's not moving along the y-axis, then we know that the normal force is equal to mg, right? Because if we were to look at the car from behind, remember what I said earlier, Fn, Fg, and if you're making that right turn, right, then your static friction force is along the left, or to the right here, basically. So Fn is equal to Fg, because this car is not moving along the y-axis. So then we have the mass, right? So we can just take it, multiply it by 10, and that gives us our normal force. So 1500 times 10, right? That's our normal force, times our radius, right? That's 20 meters. And then times our coefficient of friction, and then divided by our mass, take the square root, and that's how we can get our speed. That's a good example there as well. Mm-hmm. Mm-hmm. So yeah, for static friction force, there's kind of like two components or two concepts with static friction force. So static friction force is the force that keeps an object kind of static and prevents it from slipping and sliding. And in the case of like cars and wheels, right, with tires and stuff, we can think about static friction force, right, being the grip force between the tires and the surface, right, or the road. And then that's the kind of the concept that we're looking at here. So if this car is trying to make this turn, right, so if I look at the tires here and I'm trying to make this turn, well, you can think about the wheels kind of moving to the right, right? So in order to move in this circular type path, static friction force helps the wheels or the tires grip onto the road, right? If the tires are gripping onto the road properly, I can kind of think about, okay, well, if I have good grip on the road, right, with my tires, then I'm able to make this turn. If I don't have good grip, let's say like if in the winter conditions, if I don't have good grip, then I might not be able to make this turn properly, right? And so static friction force gives you that grip force that allows you to make turns. And that turn, right, to be able to make a centripetal, or to be able to make a circular path, right, then centripetal acceleration, centripetal force pointed towards the middle. And so the force that is going to be allowing you to move along that circular path is static friction, because it's the force that helps you grip and helps you make that turn. So if I want to make a turn, move in a circular path, I must have a force that allows me to move in that circular path. What force is going to allow me to grip with the road? That's static friction. If I don't have grip, if I don't have static friction, right, I'm not going to be able to make this turn. And if I'm not able to make this turn, then I don't have a circular path anymore, right? So static friction force gives you the grip on the road. It prevents you from slipping and sliding at the same time, and helps you to make that turn. So think of like the grip on the tires, the traction, right, that helps you make the turn. And in order for you to even make a turn, to go along a circular type path, right, because if you make a turn, you kind of go in this trajectory. So in order for you to make this type of turn, you have to have centripetal acceleration and a centripetal force, and that's pointed towards the middle of the circle. Now, in order for you to even travel along this pathway, you have to have grip on the tire, you have to have traction, right? That traction, that grip, that static friction helps you to make the turn. So we have to question ourselves like, okay, well, if the static friction, if that grip force on the tires, if that traction helps us to make a turn, right? Well, then it should also help us, or help provide that centripetal force, because centripetal force in and of itself helps us make a turn. So that's kind of the idea here with why static friction force is pointed the way it is, and how I guess we can define it. Hopefully that kind of cleared things up. Now, we have centrifugal force. This is like fake. This is just cap right here. This is not an actual force. It's a fictitious force. It's just basically the tendency of an object to move in a straight line. So if, for example, remember that tennis ball problem, right? If I were to cut the string, it would move this way, right? So like we can theoretically say that this is the centrifugal force, right? Because centrifugal force is just the tendency to move in a straight line. This never appears on free body diagrams, and it'll never be included in Newton's laws. Literally, it's just a concept. Forget about it. It's not an actual force. Don't even worry about it. It's just basically the tendency for an object to move in a straight line or continue along its intended motion or path. And so, like if you're moving in a car, right, if you're making a turn, you're kind of going this way, right? But without the door kind of pushing up against you, you would actually normally go this way, essentially. And so the door gives you a center-directed force, helping you move in a circle. Otherwise, you're just going to go flying north, right? So centrifugal force, don't really have to worry about it. It's a fictitious force. It won't ever appear on a free body diagram, anything like that. It's just the tendency to move in a straight line. Definitely, like, it's a concept that you should know, because it might come up like on a quiz or something like that, just to kind of like ask you if you understand what's going on, basically. And then for centrifuges, here really the only thing that you have to know is that they offer you a centripetal acceleration, spinning things really, really fast, right? So they can create a large apparent weight, and they give you a centripetal acceleration v squared over r. And so yeah, like I guess there's not really much to say, I guess, for this slide, but basically if you have the contents inside your centrifuge, if they want to go in a straight line, but the tube is moving fast, that everything goes to the bottom, basically. So that's how you can separate like different like solutions or substances that you want based on their density. And we'll get to that here in a second. Like it'll start to make more sense, but this is just a very quick kind of introduction to centrifuges and how they can create large apparent weight by spinning an object around very quickly. I mean, really, it's just, for the most part, I think it's just really normal force is the contact force that you have. But in the case of centrifuges, and we'll get to this in a second, but really for centrifuges, like your apparent weight or your sum of your contact forces in that case, really the only thing that's in contact would be like the fluid with your object, that is. And so you'll see here in a sec that the buoyancy force, right, is your contact force in that case. And that gives you, that's how we can track apparent weight. So, but yeah, we'll get to that in a sec. But otherwise, it's normal force for the most part. And if it's in a centrifuge, there's like a fluid, it's going to be buoyancy that's going to track our apparent weight. No. Those are forces like acting against, not necessarily like in contact per se, with an object. Yeah. So normal forces for like everything else, and then for like fluids and stuff, buoyancy kind of helps track our apparent weight. But yeah, this is just like an example. If you want to go over it, sure. If not, that's fine. This isn't like really super important. I think this is just kind of a real life type situation. But yeah, let's see here. So there's another example here. Car that's out of gas coasts over the top of a hill at a steady 20 meters per second. Steady 20 meters per second, that means constant speed, so uniform circular motion. Assume air resistance or rolling friction are negligible. So we have our forces here, normal force acting upwards, gravity pointing downwards, and this is a circular path. So we can see that gravity is pointing along this negative y-axis towards the center of the circle, giving us centripetal acceleration and a centripetal force. And then we can see here that if we have centripetal force, remember, is our net force for circular motion. So if gravity in this case, or if our centripetal force, right, is directed along the negative y-axis, then the negative y-axis forces must overwhelm the positive y-axis forces. So Fg has to be greater than Fn, and therefore your apparent weight is less than gravity. So at the top of this hill here, you might feel lighter than you do maybe at the bottom of the hill or something. There's a previous example too, for those that might have missed it earlier. So I check out the recording to kind of go over that. But once again, this is another example here. You'll see a lot of the roller coaster stuff. And then we have here normal force, right, is the contact force. And so this is our surface of contact. It's perpendicular. It's pushing up against the roller coaster essentially. So in this case, normal force actually points downwards. And gravity also points downwards, right? So if we want to draw the free body diagram, we draw it this way: normal force pointing downwards, gravity pointing downwards along the same axis, right? Because normal force kind of helps push up against an object, right? It gives solidity to the surface. And then we also have gravity. Gravity always points downwards anyway. But what was I going to say? Yeah, and so this is just kind of a continuation of that, where you have maybe at the bottom here, you have normal force pointing upwards, right? This is our surface of contact, pushes up against the roller coaster, gravity pointing downwards. And since normal force is pointed in the direction towards the center of the circle, that means that our centripetal force is positive in this case. And so the positive forces, the forces along the positive y-axis, should overwhelm the negative y-axis forces. So that's why our normal force should be greater than our gravity, right? Because the normal force is going to be directly kind of giving us that centripetal force and centripetal acceleration. So if the normal force is greater than the gravity, then our apparent weight is greater than our actual weight. And so that's why you feel a little bit heavier at the bottom than you do at the top. Because if we were to set up Fn minus Fg, and this is mv squared over r, this is the bottom, right? So we can see that Fn would equal Fg plus mv squared over r. So you have these two forces contributing to Fn, and so like those forces added together would give you a really large normal force, and then that's where we can see that the normal force is greater than gravity, because gravity plus another force equals normal force, so therefore it makes sense that normal force has to be bigger. Now at the top, we have negative Fn minus Fg, right? And we also have a negative centripetal force, right? Because it's pointed along the negative y-axis. It's pointing towards the center of the circle here downwards. So we can see that basically this negative Fn is going to be equal to negative mv squared over r plus Fg. And then if we divide by negative sign, right, we can get that Fn is equal to, what is it, mv squared over r minus Fg, right? And so then you can see that this force minus the force of gravity, that means that we're going to get a smaller normal force, right? So if this was like 40 and this is 30, then we get 10 here. So you feel lighter at the top, heavier at the bottom. And that's pretty much almost always the case. Mm-hmm. Mm-hmm. Yeah. So you would have yourself right here like this, right? You have gravity pointing immediately downwards, right? Gravity always points downwards. And then since this fluid is kind of like at an angle almost, right? We can think about, okay, well, if it's this way, we have buoyancy, right? Because the fluid is kind of directed this way, right? So if let's say the fluid is kind of sinking downwards, right? Because remember, like for centrifuge, we want to like usually separate substances out based on their density and stuff. So you'd have buoyancy force pointed upwards, and like if you were to have a substance that's more dense than the fluid, for example, then you'd also might have like a drag force, because in that case, if it's more dense, if the fluid is more dense or the substance is more dense, like if you're separating components of blood, right? Then if it's more dense, then it sinks. And so if it sinks, as it's sinking, there's a drag force, right? That's going to be acting against, like, because if it sinks, it's going to sink this way, because this is the tube basically. So if it sinks this way. And to oppose that sinking, we have the drag force, right? And we have buoyancy. But then gravity is always pointed directly downwards. That's a good question. Not quite sure, but I think for fluids it's tough to kind of say like there's a normal force in a sense. I don't know. That one, like, that's a really good question. I'm not really sure. I'd have to look that one up, but um mhm. Yeah, so it's moving like downwards and down to the left, basically, right? It's moving down to the left. But for buoyancy, remember, buoyancy, like for fluids, remember if you had like a fluid here in a beaker, it points upwards, right? And gravity points downwards like that. So um, for buoyancy, right, think of it as like the force almost that kind of like tries to keep you afloat in a sense. So if I'm trying to sink this way, buoyancy wants to kind of essentially help me float in the other direction. And then drag at the same time, like if I'm sinking, right? It's drag is almost kind of like my friction for fluid. It's pushing up against my intended motion. So if I'm trying to go down to the left, drag is going to prevent that motion up and to the right, and buoyancy is as well. And we can think about buoyancy as like the force that the fluid, the water, exerts itself. So like if the cell or something like that is sinking, right? I can imagine like the water or the fluid around it kind of pushing up against it to prevent it from sinking, and the drag, right, like the friction almost due to the fluid, kind of pushing up against it as well. So that's why you have, like, for forces, like we're concerned with what's acting on the object, as opposed to like what the object is doing itself. So the object is moving down and to the left, but there are forces acting against it, like up and to the right, essentially. So we're not concerned with what happens to it down and to the left in a sense. I hope that kind of makes sense, but yeah, it's a little weird. Mm-hmm. kind of running low on time. I want to make sure that I cover the quiz, but this is really like, honestly, this is just more of the roller coaster type problem. So, yep, apparent weight is less. You feel lighter at the top and heavier at the bottom. So, I mean, this here, what they have is actually, I think, a little bit incorrect in a sense, because if you were to calculate this out, like if you were to write it out like I did earlier, where you have negative normal force minus Fg is equal to negative mv squared over r, and remember we said negative here because the centripetal force pointed towards the center is along the negative y-axis. So we'd have like your negative Fn is equal to Fg minus mv squared over r, and then if we just multiply everything by -1, basically, you can see that Fn is equal to negative Fg minus mv squared over, or plus mv squared over r, right? Or if we rearrange it, then mv squared over r minus Fg is equal to Fn. So by default, our normal force has to be smaller than our gravity. And so this, they just kind of like just drew it wrong, I'm pretty sure here. Normal force is smaller than gravity here. So because if normal force is smaller, your apparent weight is smaller, and therefore you feel lighter at the top. Here, normal force is greater than gravity, so apparent weight is greater, so you feel heavier at the bottom. Well, centripetal acceleration, like the components that are contributing to your centripetal force are normal force and gravity. Yeah. Here, like, it's almost just normal force. It's just that you always can include both forces. Like, this is the axis of centripetal acceleration. Let's call it the axis of centripetal acceleration, or centripetal force. So any forces along this axis, we include it in the equation for centripetal force. That's why we say Fn minus Fg, in this case, Fn minus Fg, right? So we kind of include the forces that are on the same axis. But we can say that, in a sense, normal force, since it's the only force that is pointed directly towards the middle of the circle, it's kind of the force that is directly giving us that centripetal acceleration. But here at the top, it's both normal force and gravity that are directly contributing to centripetal acceleration. But in either case, you have to include both because they're on the same axis as the, this is not really a term, but like we'll call it a centripetal axis in a sense. Yep. Yep. Yep, exactly. Yeah. So at the top, you would be going at a speed so slow to just barely lose contact or maintain contact with the track. So if we wanted to figure out the slowest speed that we can go before we lose contact, then normal force has to be 0 because that's when we lose contact. And then we would have to solve basically for v, because we'd have negative Fg is equal to negative mv squared over r. Solve for v, and that's what you get for your minimum speed. Because that would be the speed that you travel at where your normal force just equals 0, or when you just lose contact. So that's a great question. But yeah, like I said, for this one, like this is just more of the roller coaster type problems. I can upload this slide here, but you guys should have like the answer for this and kind of the explanation for it. I just want to try and hurry up here to cover this. I'm gonna be honest, like these last couple of slides, they're important. They're not like, in my opinion, super crazy important because we never really like saw like a bunch of problems about this. So I tell you what, like I'll try to write up an explanation of what's going on for these last couple of slides because I know it's going to take me a longer time, because they have like elevators and stuff, and it's kind of a mess. And you can see like I have a mess of notes here about it. So I will cover this, like these last couple of slides. I'll just like write something up for it and upload it on Google Drive. But I just want to make sure that I'm doing as much as I can in the next couple of minutes. So I'll move on then to the quiz. So I don't have, I think I just forgot to kind of like scratch out the answers, but it's fine at this point. Like I already upload the quiz on Google Drive anyway. And I think it'd just be faster to kind of reason through what's going on as opposed to just writing everything out, because it's more important for you guys to understand what's going on. But with that being said, we can kind of start the quiz stuff here. So for number 1 here, we have bug on a record. Consider a 0.05 gram fly sitting on the very edge of a record, as shown to the right, which is not slipping over the surface of the record. The record is rotating clockwise with a rate of 0.4 revolutions per second, and the radius is 15 centimeters. So we have our revolutions per second. Remember, we said earlier that when we have revs per second, revs per minute, revs per hour, when we have revolutions per time interval, that's an indication of frequency. So frequency is 0.4 revolutions per second, right? Our speed is always in like meters per second, miles per hour, that type of, unit. But when we say revolutions per second, that just means that like, yeah, we're traveling around the circle we're making 0.4 like revolutions every second. So we're traveling, I guess, we're making 0.4 of a travel around the circle every second, essentially. So we also have our radius, which is 15 centimeters, and we know that usually we want to have things in meters per second as they want in part A. So 15 centimeters is going to be 0.15 meters, right? And we have our mass is 0.05 grams. So there's also an indication that it's not slipping, right? The fly is not slipping. So remember that record player problem I did earlier? Indication of not slipping means that there's going to be a static friction force that prevents that slippage, right? So static friction force in this case, right? So if we have that fly on a 3-dimensional plane, right? That fly, normal force up top, gravity at the bottom, and then directly along the horizontal surface of the record player, we have static friction force that prevents slipping and sliding on the actual record, right? And when we have this record type problem or disc or whatever, when you have an object that's not slipping or sliding on it, static friction force is almost always going to be the force that's going to give you your centripetal acceleration, and is going to help you to continue moving in that circular motion and prevent slipping or sliding. You guys can hear me, right? Okay, I just want to make sure because like my computer just lagged out right now and like nothing is moving. So I just want to make sure that everyone can hear me properly still. But yeah. Anyway, we have a lot of this information here. Now we want to figure out linear speed, right? So remember linear speed is v, and we know that v is equal to 2 pi r f, or 2 pi r over t, right? Since we have our frequency already, there's no reason to convert t really. We can just usually go ahead and just multiply out the frequency. So in this case they did convert it to period. I don't really see the point. So v is equal to 2 pi r f, right? We have our radius is 0.15, so we can take 2 pi times 0.15 times our frequency, which is 0.4 revolutions per second. So if we multiply that out real quick, let me check just to make sure. Yep, 0.38 meters per second is what you should get for part A. That makes sense, right? We're trying to figure out linear speed. That's all we want to figure out. And so we can do that given that equation. V is equal to 2 pi r f, or 2 pi r over t, right? We're given frequency, which is 0.4. We're radius, and we can just figure out linear speed using this equation. Now, for what force is responsible for centripetal acceleration, remember we said static friction. It's a force that prevents slipping or sliding on the record player and allows us to move in that circular motion, right? Because normal force and gravity are pointed along the y-axis, and then static friction force would be along the x-axis, right, to help turn around in that circular path. So this is pretty much going to be the case for these types of problems. Now, magnitude for the centripetal force, right? We know that centripetal force is equal to, so Fc is equal to MAC, right? So we have our mass from earlier, that was 0.05 grams, and we have to convert that actually to kilograms. And then we can multiply by our centripetal acceleration. So how can we get our centripetal acceleration? We know that's equal to v squared over r. We have our radius, and we have our speed from earlier, so we can just plug those two values in, get the centripetal acceleration, multiply it by the mass. You can see here, AC is equal to v squared over r. You plug in the v from earlier, divide by r, you get your centripetal acceleration, and you multiply by your mass. And then that's how you can get your centripetal force there. And yeah, I'm going to be uploading this document later on the Google Drive for sure. But yeah. So that's kind of an example there for the for how they're going to integrate like centripetal force, centripetal acceleration, and the period, frequency, speed stuff into one problem. Man. Now for problem 2, this is where I was talking about earlier in the year, where they like try to be cool, and they were just like integrated whatever was slapping with the youngins, I guess, because they just decided to like give us an Among Us problem, and we were just not in the mood to have this. This was just like, I didn't like this problem. Not only because of the context and like the drawing that they have, but like A was really bogus. So I'll get to that in a sec. But problem 2 here, imposter on a bike. Someone in a spacesuit is riding their motorbike inside a pipe, driving in a vertical circle at the instant shown with the person on the bike at the bottom of the pipe. The bike is moving at a constant speed. So constant speed, that means uniform circular motion. Radius of the pipe is 2 meters, so we have radius is 2 meters. And then mass is 120 kilograms, right? For this problem, take the object to consist of both the person in the spacesuit and the bike together. So that's one object there. Yeah, absolutely, no worries. Yep. Sorry about that. Thanks for speaking up and letting me know, because like sometimes I just want to cover a lot, so thanks for letting me know to slow down. Yep, for sure. But yeah, we have our radius is 2 meters, right? So from here, the bottom to the center is 2 meters. The mass of the rider with the bike, that whole system there, mass is 120 kilograms, right? Constant speed indicates uniform circular motion, right? We're going to have a centripetal acceleration. And then for part A, they want us to draw a free body diagram acting on the object at the instant shown. And we have to include subscripts and include all forces in the horizontal direction, even those that may be small. This is where they got us, because we weren't sure like what all forces they wanted for this free body diagram. But naturally, you have a normal force, right? Normal force that's acting against the weight of the object, right? Or weight of the bike and the person here, right? So normal force here equal to gravity. There isn't any acceleration in the y direction, or at least like, actually no, I take that back. My bad. Actually I made a mistake there, because you have normal force and you have gravity, but then in order to move obviously in a circular path, right, we have to have a centripetal acceleration. We have a centripetal acceleration, right? We have a centripetal force. That means that it's pointed towards the center of the circle. Our net force, our centripetal acceleration pointed towards the center of the circle. So it's pointed along the positive y-axis, right? That means that our net force, our centripetal force, therefore has to be positive, right? So that means the forces along the positive y-axis have to overwhelm or be greater than those on the negative y-axis, right? So Fn, therefore, has to be actually greater than Fg. And that makes sense because remember the roller coaster problems that we did earlier? At the bottom of the roller coaster, you feel heavier. You have a larger apparent weight, right? You feel heavier, larger apparent weight, larger normal force. At the top, you feel lighter. You have smaller apparent weight, smaller normal force, right? But here we're just concerned with the bottom at the moment. Now, when they want us to include all forces, right? Since this is a bike, right, with tires, it's going to have some traction, it's going to have some grip, right? Now, we know that the force that offers that grip is static friction force, right? Now, as opposed to the other situations where we had static friction force pointed towards the middle, well, we have to look at what exactly is going on here. Well, the bike is moving to the right in this instance, and it's also maybe, for example, moving upwards here, moving to the left here, for example, right? So static friction force helps propel you forward, right? Like if you're not making any turns necessarily, right? If you're not making any turns, like we had before with the car, you have your static friction force being the force to propel you forward. And that's why in a previous like PowerPoint or slide, static friction force is actually the force that helps you walk, right? There's grip between you and the floor that you're walking on that helps propel you forward. So in this case, since the bike is trying to move this way, static friction force is to the right. That's why they have Fs to the right. Now, since these are also wheels technically, you should also have rolling friction. Like I said at the beginning of the semester, rolling friction is almost never present. And the reason why, it's always pretty small. And so it's almost always negligible. But in this case, they wanted us to include even the forces that may be small. So I'd watch out for that. So if you have any wheels, right, any tires, any rounded type objects, motion, wheels, tires, you're going to have rolling friction, but it's very small. So in other situations where they don't ask you to include all the forces that are small, literally just forget about rolling friction because it's so insignificant. But you should also have drag. That makes sense, right? Because if you're moving in the circular path, right? Let's say this is a ramp, right, out in the open air. Well, you're going to feel like air resistance, right? The drag force pushing against you in this direction, right? You can feel the air kind of pushing or blowing against you. So if you're moving this way at the bottom point, you have drag pushing you to the left, blowing the air blowing on you to the left, kind of as your air resistance, your drag force to the left. Now, let's say, because I know the static friction thing is a little bit confusing. Let's say if I was here, well, then I have gravity pointed directly downwards as usual. I have normal force to the left because basically this surface here, this is the contact surface, so it's perpendicular, pointed towards the middle here, right? And so if this is normal force, this is gravity, right? This would be my static friction, because then I'm like trying to move upwards. So I want the bike to grip with the track and help propel me upwards, right? And then I also have drag, like this, basically F drag, F drag. And then I have rolling friction as well, opposing my motion upwards. So that's how it would look like in that position. Now, if we were in this position, for example, you have normal force pointing downwards as well, because this is your surface of contact. The surface pushes up against the bike and the person. You also have gravity downwards like this. If I'm trying to move to the left, static friction force is to the left, propelling me to the left. And then we have drag, the air blowing on me to the right, as well as rolling friction, preventing my motion to the right. And that's a little bit different. The static friction force is a little bit different in this case compared to the static friction forces that we had earlier with other examples, where if you were turning, for example, right, with a car, the car was gripping the road, and static friction force was pointed towards the center, right? And so that is a different scenario, and so it just kind of depends on the scenario that you're looking at. So since you want to be propelled forward in this case, right, then static friction force points directly to the right. Same as if you're still traveling with a car to the right. Static friction force points to the right to help you grip with that road, propel you forward, basically. Now, with that turn, that grip force helps you make that turn. So that grip helps you make the turn, and then that grip is due to static friction. And in order for you to make a turn, you have to have that static friction to help you move in a circular path. This is slightly different, very unique situation here because it's like, it's kind of weird. I don't know exactly how to explain it, but in a sense, the wheels aren't now I get it. So the wheels aren't turning exactly. The wheels aren't turning. Like your wheels, like if you were to imagine yourself on this bike and you're moving in the circular path, you're not turning the bike left to right. You're not turning your wheels left to right. You're keeping them steady, straight, but you're moving in this circular path. Now, if you were in a car and you're trying to move to the right, if you want to make a right turn, well, you turn the steering wheel to the right, and that turns the wheels to the right. So if you turn the wheels to the right, you have that static friction force pointed towards the middle to help you grip and make that turn. Now, since you don't have any real turn here, the path is circular, but you're not specifically turning the wheels themselves. And so you're still moving in a straight line. So if you're moving in a straight line, your static friction force would just be moving the direction that you want to move in to help propel you forward. Does that make sense? Does that make sense to everyone? I'm just asking. I just want to make sure that it kind of checks out with you guys. Okay, cool. But yeah, that's kind of how we would set up the free body diagram at the bottom. Now, they said at the instant shown, the bike is moving at a speed of 12 meters per second. What is the normal force on the object at the instant shown? So we have speed, right? How do we relate that to forces? Now, we know that speed often relates to forces, especially when we have centripetal force, right? So we know that our centripetal force is equal to MAC, and our AC is V squared over R, so MV squared over R. So how can we relate the centripetal force to the forces that are going on here? Well, the normal force here is pointed towards the center of the circle, right? It's the force that's directly contributing to our centripetal force. But at the same time, there's other forces on the same axis, that's gravity, right? That are going to be affecting the centripetal force that we have. So, if we know that Fc, which is our F net, right? So Fc is no more than just your net force, but when you have centripetal or circular motion, right? So centripetal force isn't like an actual force on its own. It's just a description of what's going on, basically, especially when you have circular motion. So it's like our net force in the circular motion. And then this is equal to, you guys, wait, hold up. You can see what I'm writing and you can hear me, right? Okay, I just want to make sure. For some reason, everything is acting up today. So F net is equal to Fc, right? And so we have Fn minus Fg, right? Those are the two forces along our quote-unquote centripetal axis here, right? Those are the forces that are pointing along the same radius here, right? And so we know that this is equal then to mv squared over r, right? This is the centripetal force. So we know that speed is 12 meters per second. And then we can figure out our centripetal acceleration because we have the radius from before, right? We were told that the radius was 2 meters. So we take 12 squared divided by our radius 2 meters, right? We can get our centripetal acceleration. So mv squared over r. If we get that part, we can multiply it by our mass, which was 120 kilograms, right? So if we have the mass times the centripetal acceleration, this should be AC, by the way, we can then set it equal to Fn minus Fg. And so This is mv squared over r, right? And so our normal force would then be equal to mv squared over r plus fg. And so you just plug in your mass times the centripetal acceleration that you figured out using the speed and the radius of 2 meters, and you add it to the force of gravity. Now, the force of gravity, we have the mass of 120 kilograms, so that should be 120 times 10, right? And so this would be 120. This would be 12 meters per second squared divided by a radius of 2 meters plus 120 times 10. And this is exactly what's going on here. 120 times 12 over 2 plus 120 times 10, right? This is our mv squared over r plus fg. And so we can then figure out the normal force, and it turns out to be 9.84 kilonewtons. You can just have it in newtons if you want. No worries there. But that's how you relate. Okay, you think about speed and forces. Well, how do speed and forces relate? Well, since we have a centripetal or circular motion, right, then there must be a centripetal acceleration. Centripetal acceleration is dependent on speed. Well, if there's a centripetal acceleration, there's a centripetal force. What components make up that centripetal force? Fn and Fg, right? And so then I can relate those two forces to my centripetal force, and therefore my centripetal acceleration, and therefore my speed. So that's how you'd go about doing B. For C now, it says at the top of the pipe, at the location of the dot in the figure, the bike is still moving at the same speed it was at the bottom. Is the normal force on the object larger, smaller, or the same size at the top? You do not need to solve for the exact value, but you must justify your answer for credit. So, at the top of the pipe, what's going on? Well, we have Fn directed downwards, and we have Fg directed downwards, right? We already said that earlier. So we have Fc, which is our centripetal force, and that's our net force, is equal to negative Fn minus Fg, and then that's equal to mv squared over r, or negative mv squared over r. And that's negative mv squared over r, negative because the centripetal force is directed along the negative y-axis, so we should add a little negative sign to indicate the direction of the centripetal force there. So in that case, we can see that Fn is equal to mv squared over r minus Fg, right? So we have two equations here that we can compare. The speed here is the same as the speed here. Radius here is the same as the radius here. Gravity here is the gravity here. Well, then how does the normal force compare? And that's the question that we're looking at, right? Fn is equal to mv squared over r plus Fg, and then Fn is equal to mv squared over r minus Fg. So we have two components here that add up to each other to give us a normal force, and two components here that are subtracted from each other to give us normal force at the top, right? So this is top, and this is bottom. Well, since the speed is the same, mass is the same, radius is the same for both, these would be the same values, and these would be the same values as well. So if you subtract values, you're going to get a smaller normal force rather than a larger normal force. So if, like I said, you don't have to calculate, but if you were to think about this in numbers, right? If we said that this was 30, if we determined the mv squared over r was 30 newtons, if we did that, and the gravity was 20, for example, well, then 30 plus 20 is 50, right? Sure, that's what we got that from the past part B, for example, right? Now, the question here is that if I were to take that same 30, right, which is dependent on my speed, mass, radius, right, this was the same magnitude, but instead I'm subtracting my gravity now, 30 minus 20, well, then I get a normal force of 10 newtons, right? So I can see that the normal force is decreased. Now, it makes sense because at the bottom, normal force is contributing to your centripetal acceleration here directly. And so normal force is directed along the radius here. It's pointed directly radially inwards. It's giving us centripetal acceleration, right? And so if it is doing that, right, then normal force has to be bigger than gravity, right? Has to be bigger than gravity because it's pointed towards the center of the circle, giving us centripetal acceleration, giving us centripetal force. So if it's directed along the positive y-axis, if the centripetal force is directed along the positive y-axis, then the positive y-axis forces must be greater than the negative y-axis forces. So that means Fn has to be greater than Fg at the bottom. Well, what about the top? We have Fn towards the bottom and Fg towards the bottom, right? So both of them are directed downwards on the negative y-axis. So in this case, right, we have to look at, okay, we have to set up this equation and see. How do they compare? Well, normal force in this case and gravity are both contributing to the centripetal acceleration because they're both pointed radially inwards towards the center of the circle. But we can see by the manipulation of the equation here, we said negative Fn minus Fg is equal to negative mv squared over r. If we set it equal to Fn, we can see that Fn will have to be smaller than Fg because something minus the force of gravity will give us normal force, right? So like a value minus the force of gravity gives us normal force. So we can see that normal force has to be less than gravity in this case. Well, if normal force was greater than gravity, and all of a sudden it's less than gravity, then there was a decrease in normal force. So at the top, the object normal force has to be smaller, right? And they say the normal force is smaller at the top. At the bottom, the normal force must both provide centripetal acceleration and fight the effective weight at the bottom. This is what I was talking about in the previous slides and stuff, because they're on the same axis. Normal force is directly applying centripetal acceleration or giving us a centripetal force, but it has to fight the effects of Fg. It has to overwhelm Fg. They're on the same axis, but really normal force is the one that's directly applying a centripetal acceleration. But we still include both when we're figuring out our centripetal force. We have to include both, but we just have to keep in mind that normal force is the one that's like, quote unquote, directly applying the centripetal acceleration and centripetal force, but gravity is just going to be fighting the effects because they're on the same axis. So with that in mind, right, we can see that at the bottom, normal force must provide centripetal acceleration and fight the effective weight. So the normal force is greater than centripetal force. But at the top, normal force only needs to provide part of the centripetal force, while the weight provides the rest. So the normal force is less than centripetal force at the top. So here, normal force has to really push hard to overwhelm gravity in order for it to provide a net force, a centripetal force towards the center to keep us moving in a circular motion. But at the top, since normal force and gravity are directed downwards, they kind of share the responsibility, right? They share the responsibility. So neither one has to so normal force isn't working against gravity anymore. They're working together to both offer a net force, a centripetal force downwards, right? A negative net force or a negative centripetal force. So normal force then has to put in, quote unquote, less work, right, to give us that centripetal force downwards, right? And I would prefer to actually use equations here to kind of show what's going on, because it just helps to show that you're understanding. You're able to apply equations through conceptual thought, as opposed to just this writing here, because you can still do this, that's fine. But if you rely solely on concepts without like an equation, if you just mess up the concepts, then you have nothing to like show your work for, basically. So like maybe you misunderstood something, you messed something up, but you wrote your equation down. So I would highly recommend writing an equation for these types of problems, just to show like how you're relating numbers and like variables and stuff to what's going on logically. But yeah, that's C as well. Hopefully that makes sense. But yeah, we have 10 minutes left, so I was going to go over the rest of the problems from the online. I think I went over 5, 6, I want to say 9, 5, 6, 9, 10, so that's 4 of them, and I went over problem 2 as well in the last homework session. I can really quickly go over one. For example, this is really conceptual here. So we have 4 particles travel along circular paths of different radii with different linear speeds. So for which particle has the shortest period of motion? Well, we were concerned with period, right? And how does it relate to v and r? Well, we know that v is equal to 2 pi r over t. So if we want to isolate t and look how it is affected by the rest of the variables, we can say that t is equal to 2 pi r over v. We just multiply this over and divide v, right? So which particle has the shortest period of motion? Well, if we know that t is equal to 2 pi r over v, right? You can say that if v is 1, r is 1, then you just get t is equal to 2 pi r over v for the first one. Now about the second one. T is equal to 2 pi, same r, but now 2v, right? So that's saying that's like almost half the original period, right? That's like half the original period. How about particle 3? We have t is equal to 2 pi 2r over v. So that's saying like twice the original period, because we just multiplied this by 2 basically, because we did 2r. And then we can look at this one as t is equal to 2 pi 2r over 2v. Well, these 2's cancel out, and you're left with 2 pi r over v, which is our original. So 1 and 4 actually have the same period. But this has twice the period, and this has half of the period. So we can see that particle 2 has to have the shortest period of motion. For the particle with the longest period of motion, well, that would just be 3, right? Because it has twice the original. And then for which particles have the same period of motion, we already said that was 1 and 4, right? Because 2 and 2's cancel out, you'll be left with 2 pi r over v. Does that make sense for number 1? Yes, no? Hoping it does. You guys can hear me, right? I just want to make sure, because like I'm getting like beach balls everywhere on my Mac, and I don't know if it's working anymore. Okay, hold up. Can you guys hear me still? Okay. Okay, this is weird. All right, let me just check. Can you guys hear me? Okay, I don't know what's going on, but I will just continue with this last couple of problems, I guess. Those who are going to be watching this on YouTube will just hopefully be able to benefit from this last couple of seconds. I don't know, I can't hear any of you guys, so I sent a message in their group me, and I can't see anything from the chat. For some reason, nothing is updating. Okay, awesome. Finally, yeah, I can hear you. Okay, good, because for some reason, nothing is like working anymore for me. Anyway, that's one. I did it 2 before. 3, a jogger is running on a circular track with radius of 30 meters if the jogger completes 1 trip around the track in 63 seconds. Oh, you can't see the screen? Okay. Well, let me try and share it if I can, because everything is lagging for some reason. Okay, I for some reason cannot share my screen anymore. There's nothing working for me on Zoom. I don't know what's going on, but I mean, we only have 4 minutes left anyway. I'll just like continue like solving problem 3 from the online homework just verbally at least, and you guys will be able to see it anyway on YouTube. So I don't know why I'm not able to do anything or control anything on my computer anymore. It's weird, but for problem 3, a jogger is running on a circular track with a radius of 30 meters. If the jogger completes 1 trip around the track in 63 seconds, what is her average speed? So if we're looking for speed, right, 2 pi r, and then since we have this information that says completes 1 trip around the track in 63 seconds, then we know that that's the period, right? Because the period is the amount of time it takes for us to travel 1 time around the circle, basically. So that's 63 seconds. Then we know that v is equal to 2 pi r over t. We just take 2 pi r over 63. We should be able to get 3 meters per second. And then for which of the following gives the magnitude of the average velocity over the entire run of an athlete running on a circular track with a circumference of 0.5. That athlete runs a total length of 1 kilometers in a time interval of 4 minutes. So let me read that again. Magnitude of the average velocity over the entire run. So circumference is 0.5. And total length is 1 kilometer. Okay, so that makes sense. So if the circumference is 0.5, so the total distance around is 0.5. So let's say they started here, traveled like this, that's 0.5. If they traveled 1 kilometer total, then they just went like this, 0.5, and another 0.5. So for the velocity is displacement over time, right? So it's the final minus the initial position. Well, he ended up, or she ended up, whatever, at the same position, right? So if they ended up at the same position as before, then really their displacement is 0. And so regardless of how much time they spend running, their velocity is 0 because it's based on displacement over time, not the distance that they traveled. So if it was average speed, for example, yes, then the total length would be 1 meter divided by 4 minutes, right? And we can convert minutes to seconds to get our speed. But since it's velocity, it's concerned with final and initial position. And so since they ended up the same position, it would just be 0. But yeah, that's 2 more problems, I think. And I already went over, or I didn't go over problem 4, but that's like 7 out of 10 problems that I've reviewed on the online homework so far. And it's 8 o'clock, so I don't want to keep you guys any longer, honestly. So I'll probably just end the session here. But that's pretty much it. Hopefully you guys found this session helpful with the quiz and the review of the concepts and stuff and some of the online homework problems that I went over. But I'm just hoping, like, the more we do, like, obviously I won't be able to get to everything every single time. But the more we do of the conceptual stuff, hopefully you guys will be able to have a stronger understanding of what's going on. But yeah, that's been it. See you guys.